Our first speaker, we're very happy to have from Berkeley, Hannah Larson, talking to us about cohomology of moduli space of curves. Thank you, Hannah.
All right, thank you so much. And a big thanks to the organizers for putting together the conference, because I've been looking forward to this one since the last one, and it's really special to be back and here with everyone. So the work I'm going to tell you about today is all joint with Sam Payne and Samir Canning. And I really love getting questions during talks. So if you have any questions, please ask me anything at any time. So the story of the moduli space of curves starts with Riemann back in the 1850s. And he was interested in classifying all smooth, proper algebraic curves over the complex numbers. Nowadays, we also call this a Riemann surface. And the number of holes here is called the genus of the curve. And Riemann said in order to understand all curves, we should consider a space called the moduli space, MG, where each point corresponds to a different curve of genus G. And for reasons that might become clear later in the talk, sometimes we also care about a curve together with a collection of points on it. So I'm going to define MGN to be the moduli space where each point corresponds to a genus G curve together with n marked points. Let's call them P1 through Pn. So those are labeled and they have to be distinct. And the main goal of my talk is to understand the geometry of these spaces, MGN. So let's start off with a few examples. So in genus 0, there is just one curve. It's P1, or the Riemann sphere. And there's a large group of automorphisms that acts on this curve. So much so that if you have any 3 points, I can take them to my favorite 3 points, which are 0, 1, and infinity. And so M03 is just a point. But as soon as I have a 4th point, well, I could act and take the first 3 to 0, 1, and infinity, but now the possibilities for where that last point are parameterized by P1 minus 0, 1, and infinity. And in genus 0, as I continue adding more and more points, all of the moduli is in the location of these points. However, when we go up to higher genus, we start to see moduli in the underlying curves as well. So in genus 1, you might know that every genus 1 curve is expressible as the complex plane modulo some lattice. So just thinking, if I translate by anything in this lattice, I can get everything into this shaded region, but opposite edges are identified. So that wraps up into this genus 1 surface. And the origin is going to correspond to some marked point on it. And if I use different shapes of lattices, I get different underlying curves. So I get the same curve, C mod lambda is isomorphic to C mod lambda prime precisely when lambda prime is a scalar multiple of lambda for some non-zero number t. So it follows that the moduli space M11 is the set of lattices in the complex plane modulo this equivalence relation, where two are equivalent if I can scale one into the other. And the theory of modular forms and modular functions says that this set is in bijection with the complex numbers by something called the J invariant of this curve. All right, any questions so far about this moduli space? Well, you can see that in the description that it has come to me, I do have the data of a fixed point. For technical reasons, we often avoid talking about the moduli spaces of curves when the curves involved have infinite automorphism groups. But if I fix a point on a genus 1 curve, then there's no automorphisms. Any more questions? So as the genus, a number of marked points, grows, these spaces become more and more complicated to describe. But we do know that in general, MGN is a nice irreducible space of dimension 3G minus 3 plus n. But there's one way in which MGN is lacking, which is that if I have a family of smooth curves, the limit of that family might not correspond to a point in the moduli space. In other words, this space, MGN, is not compact. We see this already in our first example, M11. So you might wonder, well, what happens in this picture as I send the J invariant to infinity? As I do that, there's going to be some loop on this genus 1 curve that is going to start shrinking down to a point until, in the limit, I arrive at this singular curve here. And this singular curve is built by taking a smooth curve of genus 0 and gluing together 2 points on it. So this provides the first hint of a very important idea of Deligne and Mumford. Which is that we can compactify MGN, so sit it inside of some larger space, MGN bar, by allowing some singular curves to arise as limits. And these singular curves we allow are going to be nodal curves with a further technical condition called stable. So a nodal curve is just a curve that's built by simply gluing together smooth curves. And this condition stable means that whenever I use a piece that is genus 0, it has to have at least 3 special points on it, like this one. And when I use a piece of genus 1, it has to have at least 1 special point on it. And this gets back to the earlier question where I said we want to be considering curves that have finite automorphism group. So that takes care of that. So in this example here, M11 bar is M11 union a point at infinity that corresponds to this singular curve. And so, in fact, that's C union infinity, which is a copy of P1. So we'll get a more vivid picture if we look at a slightly larger example. So I want to draw now for you a picture of M20 bar. So a general point in this moduli space corresponds to a smooth genus 2 curve. But as we wander off towards the boundary, the curves can become singular. So one way that can happen is that I can glue together 2 genus 1 curves at marked points. And another way that can happen, which I'll draw in blue, is that I could take a genus 1 curve and glue 2 points together. And as suggested in this picture, the 2 pieces of the boundary meet each other. So they will meet when I have a curve that looks like this. This is built by taking a genus 1 curve and gluing it to a genus 0 curve, which then has 2 other points glued together. And it turns out that this blue piece over here actually crosses back on itself. Those are going to correspond to curves where I take a genus 0 curve and glue together 2 pairs of points. So far, what I've drawn for you is a generic 2-dimensional slice of this moduli space. But if you look back at my dimension formula, you'll see M20 bar is a 3-dimensional space. So everything in this picture is actually dimension 1 more than what I've drawn. So this green part here is in fact a whole curve's worth, as is the purple. And the place where these 2 meet corresponds to the curves that look like this, where I take 2 genus 0 curves and glue them together, and then glue together 2 points on each of them. And this point over here where green crosses back on itself is also a special point in the moduli space. Corresponds to where I take two genus 0 curves and I glue them together along 3 marked points. So now I hope you start to see the motivation for these marked points. They're exactly what allow us to glue up our curves in order to get the singular curves that arise in the boundary of this moduli space. And you'll also notice that as I go deeper and deeper into the moduli space, the pieces that my curves are built out of become simpler and simpler, all the way down until they're built out of just genus 0 with 3 marked points. But there's a trade-off as we do this. The combinatorics of how I glue those pieces together becomes more complicated. So are there any questions at this? Yeah, Rohini. If you sort of eyeball it, you should see that as I smooth out this node, I can become a curve that looks like green. Do you see that? Yeah. Right. So I should say this picture is has a little bit of artistic license in it, in that this is a stack. And so really, really, I mean, when I draw this, I mean something that looks like this modulo some finite group action. But I feel it's still fine to, it's sort of crossing itself here because I could smooth out either one of these two nodes. But of course, they're the same branch once I quotient. Yeah. Any more questions?
So the main component, I can't actually get,
Huh? So yeah, there's that big, are you talking about the big white part? The genus, just the smooth genus 2 curves? Okay, yeah, there's just sort of this part in the middle here. This is some like full dimensional open subset. And anywhere you are in the picture, you can kind of deform out into that open. So you can check in all of these pictures I drew, if you were to smooth out all of the nodes, you should see something that looks like a smooth genus 2 curve. Right, yeah. If you deform randomly, you get into the black part, and then, if you're here and you deform in a very special way so that you go along the direction of that green curve through it, then you stay somewhere in the boundary. Mm-hmm.
The open part, is it a rational variety?
For genus 2, it is. And that's actually, it's a very interesting open question. For which G and N is this rational or not? And that's something that people have been making a lot of progress on over the. Right, it's open. Well, so I should say for most genera, this we know is not rational. In fact, it's general type, and I think the going bound is genus 22 at the moment. So G greater than or equal to 22, it's going to be general type. And then I'm not sure how high people know rationality. It might be around 10-ish. And then people study unirationality, uniruledness, and there's some gaps where we don't actually know in the teens.
So in genus 2, there's like 3 invariants, just like there was 1 invariant for genus 1.
You could think of it that way, yeah. The fact that it's a rational variety says I could really put down some coordinates at least to describe a dense open, yeah. But not so once the genus is larger. Yeah. yeah, this picture gives us a good combinatorial understanding of the moduli space, but it doesn't tell us much about its topological properties. And so what I want to turn to next is the following question, which is, what is the cohomology of MGN bar? And I'm going to ask this with rational coefficients, and here I mean singular cohomology. So you should just think of this as some measure of how non-trivial a topological space do we have. People are also interested in asking this question without the bar, and the two questions are related. In theory, you should be able to pass information between them, but doing so involves the combinatorics of this stratification. So this is a very ambitious question, and so I want to start with something simpler, which is, what even are some elements of the cohomology ring of MGN bar? And the classes I'll tell you about were introduced by Mumford in the 1980s, and these are called tautological classes. So, oh yes, question, please. So we define cohomology of stacks using equivariant techniques, but I'm not involving that at the moment. When I write it like this, I'm not necessarily having to present this as a quotient. But let me say, since I'm using Q coefficients, which is it's a really nice thing to do if you're going to work with the cohomology of a stack, you don't have to worry about some of these stacky subtleties. So this singular cohomology is actually the same as the singular cohomology of the coarse moduli space, if you prefer to just think about that. Although, as you're about to see, I'm going to sort of conflate the two and assume that there is a universal family. So as we were saying, the moduli space, especially as the genus grows, is very complicated. And so it would be very hard to sort of write it down. And more or less, the only thing we really know is that each point in this space, MG, corresponds to some curve of genus G. Maybe this point to another curve over here. So I want you to imagine fitting together all of those curves I've drawn above. And this is something that maps to MG. It's called the universal curve. And you might be able to convince yourself that this universal curve is in fact MG1. Because what do I have up here? Well, I have a curve, and I have the data of a point on that curve. So this is some sort of complicated nonlinear object. And so what we're going to do is what you should always do when you see one of those, which is try to find a linear approximation to it. So picture at each point the tangent space to that curve at that point. So that is some one-dimensional vector space. And these spaces, as I vary over mg1, fit together into a line bundle, which we call omega, or actually omega is given by using the duals of these spaces. And once I have this line bundle, I can cook up a cohomology class. Then I take the first Chern class of this line bundle. That's something that measures how non-trivial that line bundle is, so how much those one-dimensional vector spaces twist around. And that lives in H2 of mg1. And it turns out that this can be extended suitably over the boundary. So I get this class in mg1 bar, which is called the psi class. Now, if I want to get a class on mg bar, what I could do is I could take powers of this class, psi, and then push forward along this map. So when you account for the degree shift in pushing forward, this is going to land in H2i of mg bar. And this class we call kappa I. Are there any questions about these psi and kappa classes? So they're called tautological because you see they sort of fell out of the very definition of mg as the moduli space of curves. All we really used was the universal family over it. So now I'm going to tell you how to produce a bunch more cohomology classes from these ones. And this is going to follow 4 steps. And the order of these steps does matter. And they're going to take advantage of the maps that we have between different moduli spaces of curves. So the first step is to take forgetful pullbacks. So what I mean is that I have a map from mgn bar to mg bar that just forgets the data of my marked points. And so I can take my kappa classes down here and pull them back up to mgn bar. So I'm going to write kappa I tilde for the pullback of kappa I, which lies in H2i mgn bar. And then I've also got these forgetful maps I'll call fi to mg1 bar. So this is the map that forgets all but the ith marking. And I could then pull back the psi class along fi. And that is a class that I'll call psi I tilde, which lives in H2 mgn bar. Oh, yes? Oh, Oh, sorry, thank you. Should I rewrite, tell me what I should rewrite. Kappa class? Got it. So, okay, let's do this again. And I'm defining good. And how do people feel about psi I? Okay, great, thank you. All right, so that was step 1. Step 2 is that we get to form the monomials in what we've already got. So in these psi and kappa classes. And then step 3 is to take push forwards along gluing maps. So we saw over here lots of examples of gluing maps. And the thing that we're going to do is whenever we have one of these gluing maps, maybe I'm going to glue something like this. I am going to throw in the image of the push forward of 1. So a multiple of the fundamental class of this boundary stratum. And then additionally, I might use what are called decorations. So use these monomials that I have. So I'll pull back from this M21 bar factor some monomial, maybe like kappa 1 tilde, psi 1 tilde. And then from the other side, I could also pull back some monomial, multiply those together, and then push that forward. And this is what we call a decorated stratum class. And that's because if I use the decorations 1, it really is just the class of a boundary stratum. And the fourth and final step is that I get to take Q-linear combinations of decorated strata. And when I do this, it turns out that the collection of classes I get is already closed under multiplication. And this collection of classes is called the tautological ring. And that's denoted RH star MGN bar inside of H star MGN bar.
The multiplicative structure of this ring known in the sense that you multiply two classes to understand what it is of a linear combination of.
Yes. So in fact, there's an algorithmic rule for intersecting any two decorated strata. So if you just think about the fundamental classes of of boundary strata. When the two pieces meet transversely, it'll be the class of their intersection. If they don't meet transversely, then there's something called the excess intersection formula, which tells you precisely the answer to this question you've asked. Now, there are lots of known relations among decorated boundary strata. These are called Pixton's relations, which generalize the Faber-Zagier relations. And conjecturally, people believe that these known relations are all relations, but that is still an open question. The way I like to think of the tautological ring, though, is that these are the classes that we know about. Like we sort of cooked them up by this very reasonable recipe that just fell out of the very definition of the moduli space. And it contains a lot of the natural classes you might think to write down, like the Chern classes of the Hodge bundle or the Chern classes of the tangent bundle to the moduli space. Yes, thank you. In fact, I was going to say that. So let me just put a note. This will be helpful. That the tautological ring is 0 for k odd. And that's because you see I started with these psi and kappa classes that lived in even degrees. Everything I did was pushing forward along some gluing map, which is going to take an even shift because these are all complex subvarieties. More questions? So the tautological ring is the classes that we are sort of know about, that we're familiar with. And a question that's really interested me lately is what else is out there and where is it? So let's ask in particular for which triples k, g, and n do we have hk mgn bar equal to rhk mgn bar? So the answer to this question is known in a couple small values of k. So equality holds for k equal to 0, 1, 2, 3, and 5 by Arborello and Cornalba in 1990. So you'll notice that they missed 4, but they did get 5. So why is that? Well, it turns out this question is quite a bit easier when k is odd, because then we're just asking for the vanishing. And so Arborello and Cornalba said in this original paper they expect that equality should hold for k equals 4, but sort of the combinatorics involved in running their same method was too intricate to carry out. But progress has been made in the next odd degrees. So more recently, for k equals 7 and 9, Bergstrom, Faber, and Payne proved that equality holds in these cases, which again is just vanishing of the cohomology for these odd values. But then it is known when k equals 11 that H11 is not always 0. So H11 M111 bar is non-zero. And the fact that this cohomology group is non-zero corresponds to the existence of a weight 12 cusp form for SL2Z. But you could still ask, well, all right, I know about this cohomology in degree 11 here. I can certainly pull it back to the M1 ends with n greater than or equal to 11, and that will give me some more cohomology classes. Is that all of the ways that you can build something in H11? And it turns out the answer is yes. So this is our first theorem. And that is that H11 of mgn bar is equal to 0 for all g and n, unless g is 1 and n is greater than or equal to 11, in which case it is generated by the pullbacks along the maps that forget all but 11 of your points. And we also know the relations among these different pullbacks that you will get. So I think this vanishing, though, in genus 2 or more was a little bit of a surprise, because people sort of saw this class in genus 1 and thought maybe that, H11 is always non-zero. So we also have a result for degree 13. But before I state that, I want to tell you how to think about it. So this is in terms of a new definition that we made. I'm going to say that the semi-tautological extension generated by a collection of classes in the cohomology of mgn bar is the output of running steps 1 through 4, starting with the psi classes, the kappa classes, and these new alphas. So you should think of this as sort of the decorated strata you can build, but where you also allow alpha classes as decorations and the pullbacks of them. So our theorem for degree 13 is that H13 mgn bar lies in the semi-tautological extension generated by H11 M1 11 bar. This is for all G and N. Oh, yes, please.
Yeah, sorry. You've got this one special thing which comes from this 12 form for LTZ, which is like a really special thing, right? What is the kind of thing I should be thinking of as an alpha?
Yeah.
Semi-tautological.
Right. So yeah, you should be thinking of, at the moment, alpha as being just a class in this H11 M111 bar. Yeah. Or maybe like take a basis for this. This is actually a two-dimensional space. It has Hodge type H11 0 plus H011, and our cusp form corresponds to a holomorphic 11 form. But yeah, you could really start with anything you like, and maybe by the end I'll give you another idea of what you might try to throw in. Any more questions? Yeah, Juliet.
Is there a third tautological result which says that if I take my alphas be everything below, then it generates everything above? So like here you said, oh, I just need to take the generator for H111.
Right. So yeah, let me also say we do have a general result of maybe of the flavor you're imagining, which is for any k, there exists a finitely generated semi-tautological extension containing HK mgn bar for all G and N. And I can give you precisely, this is effective. I can tell you what some maybe very large collection of cohomology groups you would have to throw in. But this sort of general result, at least in these first few cases, seems to be much further from what's actually needed in practice. Yes. And in fact, I would like to end by telling you about some results that we've gotten in even degree using this idea of semi-tautological extensions. Yeah. Yeah, so I would say rather that those are good candidates to plug in to this framework of semi-tautological extensions. We're not answering exactly like what is the minimal amount of stuff you have to throw in and where exactly is it. We have sort of some ideas on what you need to throw in. But I think that's very interesting, and that's sort of what this definition is begging of us next. Yeah, another question? No? Oh, yeah.
Is there any known cohomology that can trace back to
Yes, so there is some stuff in H15, M115 bar, and then going up on all of the odd M1Ns, there's going to be classes that correspond to cusp forms that are not pulled back from lower numbers of marked points. And we also know that there's some H17 M214 bar. And then sort of you know, not really sure what's happening in higher genus. All right, so I'll end by saying a bit about even degrees. So far, all of the non-tautological classes that I've shown you live in odd degrees. But it turns out there are also some known non-tautological classes in even degree. And these have a very geometric origin. So I'm going to define BG to be the collection of curves in MG that admit a degree 2 map to an elliptic curve. So this is very appropriate for spec Q bar because these curves are called bi-elliptic curves. And if I take the closure of this locus in MG bar and I take its fundamental class, I get this awesome queer cohomology class that lives in even degree but is not tautological. As soon as G is greater than or equal to 12. And we have some reason to believe that these might be the sort of first examples of non-tautological classes in even degrees. So the ones occurring in lowest even degree. So yeah, it seems reasonable to conjecture that HK MGN bar should be equal to RHK MGN bar for all even K less than or equal to 20. And then the first occurrence of this is happening at genus 12. It's living in H22. So we've made some progress towards this conjecture. Which is, first of all, we've settled the case of H4 from Arborello and Cornalba. It's equal always to the tautological ring. And this is really using a different idea than what Arborello and Cornalba originally outlined. It's going off of this general theorem that I stated. Oh, yeah? Yes. Yeah, so the techniques for Bergstrom, Faber, and Payne are very similar to Arborello and Cornalba. It's this sort of inductive procedure, and the real new contribution there was understanding some new base cases, particularly in genus 4 with low numbers of markings. So to get up into degree 11, we needed to understand a lot more base cases. And, well, we had an issue that one of our base cases didn't vanish. But again, this result does sort of build upon the ideas of Arborello and Cornalba, whereas this one is sort of taking a new path. And I'll note this implies that H6 of MGN bar is equal to RH6 for G greater than or equal to 10. This is by a result of Harrer. And then the final thing I want to say is that for k less than or equal to 14 even, we have shown that h lower k mgn bar equals rh lower k mgn bar. And here by h lower k, I mean h upper dimension minus k. And this result is something that follows from all the new base cases we knew about, together with sort of the dual of the Arborello and Cornalba induction. And this I view as sort of progress towards this conjecture, because it's saying now the conjecture holding is equivalent to asking that the pairing on the tautological rings is perfect. And I will leave it here and open up to questions.